So I'm going to talk about how contemporary economics intersects with some of the other social sciences to understand how economic phenomena is situated in a larger domain of social action. Okay. Different social sciences have different views about how economic phenomena fit into the broad scheme of social phenomena. So here's a rather extreme point of view. This is the Karl Polanyi, who's a famous I don't know what you call it, a historian, sociologist, variety of things, right? But clearly not an economist, right? and clearly, I think maybe a little bit. I'm not sure that his conjecture here would stand a good empirical test. But this is kind of one point of view that social action is every. Oops, I think the mic just disappeared. Social action is everything, and economics is very derivative. Now, down here I have this is a famous quote. I remember first hearing this from Ken Arrow many years ago. It was in fact written by Jim Duesenberry. Economics is all about how people make choices. Sociology is all about why they don't have any choices. Now, this sounds like some economist who's kind of spinning on sociologists, right? But in fact, and there is this belief that is fostered by both economists and by people in other academic disciplines that economics is something distinct. It clearly is distinct in terms of method, right? But we're also distinct in many other ways, and we don't draw on the other sciences and so on and so forth. And this point of view is entirely false. Okay, so for example, at the University of Chicago in the 1930s, Henry Schultz was actually colluding with is it William Thurstone, the guy who did the first Probit models, in estimating together, psychologists and economists were estimating indifference curves. Okay, there's a long history of collaboration. I mean, a good history of behavioral economics would essentially start sometime in the mid 1800s. All right. Similarly, with sociology, sociology is actually the youngest, I think, of the social disciplines, kind of really establishing itself with a distinct set of institutions, academic bodies, so on and so forth. Really much later, I think maybe in the 1920s or 1930s, even though, of course, there's an intellectual tradition that goes back very, very far. But in fact, economists have always been, have always understood, I think, that economics really does sit inside of social life. And here, Duesenberry gets stuck with this quote, right, which sounds like the great, economics and everything else kind of thing. But in fact, he uttered this quote at a conference. He said this at a conference where he was a discussant of a paper on education and human capital investment by Gary Becker back in the early 1960s. And he goes on to say that even Gary Becker, right, would not assert that he has a choice between having 2 children and educating them well and having 4 children and educating them not so well, right? So already, this is kind of a sociological critique of an economic model. And in fact, I think that there is that many economists, you don't see it in the work because our methods are so different, but there are many economists who have profitably read sociology. There are many sociologists who, or at least some sociologists who are who are indistinguishable from some kinds of economists, so rather than kind of spending a lot of time drawing disciplinary boundaries, we should be figuring out, I think, what we can learn from each other. And one of the things that we can learn is about, at a very, very, from sociologists, is at a very, I'm going the wrong way, that doesn't help. It's not to go back. We can learn at a very, very micro level how interaction works. It's always seemed to me that if we think about economics as a discipline, compared to the other social sciences, we're distinguished, I think, in 2 ways. One is by our analytic bent, as opposed to our descriptive bent. And the other is because we really are about systems, okay? And you think about a market, right, as a system, right? It's a social system. We have all these agents who interact, and somehow it's the interaction that interests us. So we talk about aggregates, right? We're interested in price. We're interested in GDP, so on and so forth, right? And on the other hand, if we want to really understand, excuse me, coughing into the mic isn't going to work. So if you really want to understand, where these aggregate comes from, we need to build disaggregated models, right? This is what the so-called micro foundations of macro movement of the 1960s and 1970s was all about. And what we find when we peer, into economic exchange in great detail, we see a lot of social action going on, right? And we can and therefore we actually need to look at the constructs of sociologists and some of the insights they have in order to understand this. So let me give you one example of this. There's a guy named Wayne Baker who is on the faculty at the University of Michigan's Business School. You might well know him. Or you should get to know him. He's very interesting. So he did, for his thesis work, he studied, I believe, at the Chicago Board of Trade. He went to one of the, I think it was in Chicago, he went to the market there, and in those days, there was a pit, and people stood around in the pit, and they called out to each other, right, and bids and asks, and so on and so forth. They had little notebooks. You can see films of this, and this is how trading in this market that we characterize. This is a commodities exchange, right? So this is exactly the kind of thing that we think about as the anonymous market. Now, how did this market actually work, right? Well, this is what Wayne Baker, a sociologist, set out to find. He sat down, or didn't sit down, he stood because you have to stand there, with a trader, and he observed who traded, he observed how trading actually took place. And what he discovered was that it wasn't the case that anybody who wanted to trade contract X dove into the pit and traded with everybody else who was there. What he discovered was, of course, no surprise that people specialized in what they traded in, but that even within the context of a particular contract, right, that any individual trader would have a set of traders that were his compadres, his partners, right? And I say his because this is a very male activity when he did this, and it may still be for all I know. So in fact, there was a network structure to trade, okay? That I might often trade with A and B, but I might not ever trade with C, okay? And now here's the really surprising thing. So imagine that you're a trader, and what you're doing as a trader is you're continually, you're carrying an inventory, right, you're carrying a position, not an inventory, you're carrying a position. You're long in some things, you're short in other things. Now what happens when the market begins to get very volatile? The market begins to get very volatile, you are very exposed. You could lose a lot of money on your longs, you could lose a lot of money on your shorts, right? And so what traders tend to do, right, when the market begins to get volatile is that they want to close out some of their positions. They want to shrink the size of their positions, both long and short, okay? So you would think, fine, the market is getting very volatile. Now, traders are looking to get some of the stuff off their books, to zero out some of their positions. So they should look for anybody out there to trade with, right? Anybody on the other side of a trade. So their trading networks, of course, should expand in a situation like this, right? What he found, of course, was that just the opposite happened, right? That in this situation, when the market is very volatile, people would trade with fewer people. That people would trade only with people that they really trusted. And if you think about what might go on in a market. Think about what we know about counterparty risk. Think about what we know about asymmetric information in the market. Right? This guy who you don't know so well comes up and offers you, and maybe you trade with occasionally, he comes up and he offers you a trade, and the market's really volatile, and you have to ask yourself, well, what does he know? Right? Is he just looking to clear out a position? Is he just looking to match me? Or does he really know something that I don't know? Or is he about to nail me to the wall in pieces? Okay? And so, consequently, what happens is that trust issues arise, right? And therefore, the trading network shrinks, right? This doesn't sound anything like anonymous exchange, right? This does not sound a lot like Bull Rock, okay? But this is exactly how the market works. If we want to understand macroeconomic performance, for instance, if we want to ask, for example, what happened, when the capital markets actually froze that day in September, right, at the beginning of the financial crisis, right? If we want to understand what happened there, we actually need to understand the trading process. So we know that supply and demand, the Marshallian scissors, this is a wonderful way of describing markets when they work well. I'm sure all of you actually understand that supply and demand is not a theory of market behavior. It's not a theory of how markets work. It's a theory, it's a reduced form theory that says, in this kind of trading environment, in this environment, when the variables look this way, when the input variables look this way, here's the prices and quantities we expect to see, right? And if we really want to understand why supply and demand works, we actually need, what we typically do now is we begin to build game theoretic models. So we look at models of auctions and double auctions and so on and so forth, right? We actually build strategic models of the trading process. If we want to understand when it is that supply and demand works and when it is that supply and demand fails, right? When the predictions go out of whack, so on and so forth, as happened at the beginning of the financial crisis, right? Then we need to understand the micro details of trade. And this is where understanding the kinds of things that Wayne Baker was observing become very important. Okay, so we have a lot of reason for looking at what sociologists do. And while I've been chattering here, you no doubt have been reading this slide. And if we look at, there's a variety of, so economists have this really horrible phrase, social interactions, right? As opposed to what, non-social interactions, antisocial interactions? I don't know. But we have this phrase, social interactions, and this is, these are different, and what we mean by this is, where is it that social concerns really begin to impinge upon economic life as we know it? Where is it they become very important? And here's a list of topics, right? All of which there are many, many papers on, and many are in the references, many are not. You can see me if you're interested in some of these areas, or you can email me and I will come up with references for you. There are a number of different, so over here I have a variety of phenomena to which the phrase social interactions has been applied by economists. And over on the right I have a number of different mechanisms, okay? Peer effects, right? We do what our friends do, or we do what our family tells us to do, right? There are people that we are closely related to, and we learn from them, or we follow them in some way. Role models, it's kind of like a peer effect, and a role model might not be somebody you actually know, but again, this is another kind of, it's kind of an imitation process. Social norms are more of an aggregate kind of thing, right? So we have norms of behavior that we do things certain ways and not other ways. Social learning, social capital, these are all phrases that no doubt you've come across in your reading, especially those of you who are interested in development. And when we went around the room on the first day, a number of you were interested in development. You hear about this stuff all the time. So these are all mechanisms that appear under this rubric of social interaction. Now, mostly today I'm going to talk about network analysis, namely because that's what I know most about. I have 132 slides. And you can guess that in 2 hour and 15-minute sessions, I will not be going through 132 slides. And I'm going to choose topics from the list that is in my slides, but you have the whole package so that you can explore them on your own. And you certainly should get a hold of me, get in touch with me, send me an email if you would like to know more about some of the topics that I won't touch on at all. I began this, when I actually wrote these slides first a couple of years ago, I just kind of wrote down everything I thought was important, and then I figured I'd sort it out at the time of the lecture, and I'm still sorting, I guess. Okay, so let's move on. How would one study social interactions? Okay, there are several different methodologies. I think the first thing that's very important to know is that if we want to understand how market phenomena, how the traditional domain of economics intersects with other kinds of social action, we actually have to read the literatures of the disciplines, right, that study these things. right? And so, for example, if you are a labor economist, you need to learn you need to read something about the world of work as seen through the eyes of an ethnographer or a sociologist, social psychologist, so on and so forth. So one research paradigm, not paradigm, but one research methodology, a place where you can learn a lot. If you're going to theorize about things, it's good to have facts to start with. Okay, so where are you going to get some facts? Okay, well, so read some ethnographies, and I've listed here some of the classics, both some classic ethnographies having to do with poverty, and some more modern ones. These mostly have to do with things in the United States because that's what I know most about. But there is, of course, a lot of international work as well. I'm not comfortable enough with that to actually make recommendations. I once asked a sociologist that I knew, how do you know when an ethnography was good and when when an ethnography is bad? Because you read an ethnography, there are lots of stories, right? And you know what we say about stories? We say anecdote. It's like a bad thing, anecdote. And but in fact, well-constructed ethnographies, actually, there are methodological principles, and I asked the sociologist Martina Morris, what made a good ethnography? And she said, so name some ethnographies that you like. And so I gave her a list. And she said, now tell me some ethnographies that you don't like. And I gave her some other lists. And she said, I agree with that list your two lists entirely. That's exactly right. She said, you know what's a good ethnography and what's a bad ethnography. So I concluded there was a Supreme Court Justice of the United States who once said, and you know what's coming now, right? That there was a trial involving whether something was pornographic. And this Supreme Court Justice said that I can't define pornography, but I know it when I see it. And ethnographies, I guess it's the same thing. When you're reading BS, okay, you know it's BS, right? And when you're reading something that's well put together and backed by appropriate data as well as carefully constructed stories, you know when you're reading them. And this is if you really seriously want to dive into this kind of work, you should be diving into this kind of literature. Another important research methodology has to do with social experiments. And I've listed some important social experiments here that were done back in the 50s and 60s. I'm actually not going to talk about these now because we don't have time. But I think it's fair to say that social psychology today is a shadow of what it once was, and social psychology used to be characterized by really deep field work, where they did things that I think that this experiment would not be allowed today. Okay, they took kids out into a state park in Oklahoma and they turned them against each other. Basically, is what happened. This experiment is very famous, but it's actually garbage. Right? It's actually fraudulent, and we'll talk about it a little later. This is a very interesting experiment, okay? And very good. And I think it was done at Stanford. Is that right? So the story is Stanford or Yale, right? One of the two. And the idea was that two people would walk into a room at a time. One of them was the subject, another one was the graduate student, right? And there were two lines that were drawn on the wall. One was shorter than the other, and what you had to do was you had to say, well, which one is the shorter line? It doesn't sound hard, right? So the graduate student would point to the longer line and say, oh, that's obviously the shorter one. Okay? Now, what do you think that the other guy did, right? That was the subject of the experiment. And of course, it turned out that more often than you would have wished, right? The subject of the experiment said, oh, yes, graduates, not knowing it's a graduate student. Oh, yes, graduate student, that's right, I agree with you. Right? So, but there is this deep and interesting tradition of field experiments in social psychology. We in economics, of course, have our own field experiments, and I've listed two here that have a lot to do with the subject of poverty and inequality. And these both actually, the control was not actually really an experiment. It was something that turned out to be a kind of experiment. But without going into any details, as a result of the court case in Chicago, the Housing Authority gave vouchers to a group of people and who were living in projects. They were moved out of the projects, and some people got to kind of stay in low-income areas. Other people were moved into the suburbs and so on and so forth. And then they were followed by, this was actually done by court order. It was actually not a carefully designed experiment. The assignment of the treatment was to some degree, but not entirely random, and so on and so forth. The findings were very interesting. The question is, if we moved people out, into wealthier neighborhoods, into neighborhoods that were less troubled, what kind of impact did this have on social and economic outcomes? And the results were somewhat striking. And so, in fact, and this actually happened, I think it was in the early 1970s. So in the 1990s, the United States Department of Housing and Urban Development said, actually, we should look at this a little more carefully. And so they designed this experiment called Moving to Opportunity. And you know more about this than anyone in the room. They designed this experiment called Moving to Opportunity, which really was an experiment in an attempt to test more carefully the effects of moving people, out of projects and into different kind of residential environments. And I'm not going to actually talk about it all, except to say that data from this is available. It's been studied a lot. This is an experimental method. This kind of large-scale experiment is, I suppose, rarely feasible unless you're a very well-connected person, but there's a lot to learn from these kinds of things. And furthermore, there are often accidents that provide what you might call quasi-experimental data. So this is another way in which one learns about social interactions. And then, of course, there's all the kind of standard stuff that economists do all the time that I'll be talking about a bit later. What kind of questions, what do I want to say here? What are some questions we want to ask about investigating social interactions? Well, one question is, the methodology of economics, is if we want to study something, we build a model, right? And then we take this model and we try to find ways of implementing it empirically. We might estimate it directly, or we might, look for some of the predictions of the model and then actually try and statistically verify them without actually estimating the model that we talked about. There's a variety of different things that we do, but it all comes down to having some kind of model of social interactions. And as you can see here, so I've made a list of different kinds of social interactions that different models distinguish. There are lots of models out there of social norms. They are game theoretic models. They all seem to be built around the idea of a coordination game. Namely that if enough of us begin to do something, then others will want to join in, okay? And so this is one understanding of where social norms might come from. There is another literature on where social norms might come from, and I'm now thinking about the work of, for example, Peyton Young, who says that if we think about the dynamics of playing a game, of having some kind of social interaction in a large population, or maybe a repeated interaction of some kind, there are some equilibria which are easier to reach than other equilibria. There are some equilibria that we will naturally tend to settle into, and these equilibria we might call the normative equilibria, the social norms. He has a nice paper on social norms and contracting, both an empirical paper with a student of his named Mary Burke on agricultural sharecropping contracts in the Midwestern United States, and also a theoretical analysis as well that appeared in JET in the late 1980s, early 1990s. I don't remember exactly, but that's what Google, or I guess here it's Bing, is for. Okay. What kinds of questions do we want to ask when we look at social? So we have social norms. Another thing, of course, is group memberships. And although we can build very sophisticated network models, and this is all the rage today, it might well be the case that networks are in some sense oversold. We have very old models, going back to Jim Buchanan and others, of clubs. which is to say that people voluntarily associate in groups. Right? And these groups provide some kinds of group public goods, club goods, right? Club goods differ from public goods because club group goods are excludable to people who are not members of the club, right? So we might actually think about people joining clubs by virtues of our characteristics, right? So you are all Chinese, I'm American, right? And it wasn't a choice for any of us. It seemed to be a choice of our parents, and or grandparents or great grandparents, right? However far back you want to go. But in any sense, in any event, just thinking about the relationship between individuals and groups without looking at the finer structure of whom is talking to whom within the group or what is knitting the group together, this is also often a very profitable path. And then finally, of course, we might well be interested in, and this is what I'm largely, as I said, going to talk about today, is how peer effects actually work, right? How are we influenced by single other individuals or groups of individuals? How do things diffuse among a community of people who are loosely connected, right? And what are the aggregate implications of that? Okay, so if we study of peer effects, there are really two different kinds of questions that we want to ask. One set of questions has to do with what goes on at the micro level, right? And I'm going to give some examples of this in just a moment. But if we go back to Wayne Baker standing there in the pit, one question is, well, just who is trading with whom? What do these trading networks look like? What percentage of traders is any one trader interested in interacting with, right? And how does that change with the environment? So we might look at each individual, we might look at individuals, traders' decision rules, and then look at and ask, what do these decision rules look like? We might ask micro questions like that. Then on the other hand, there are aggregate questions to ask. So what are the aggregate implications for market performance of the fact that people trade in networks, right? If we make the networks denser in some way, okay, if we make the networks denser, will market performance change? Will markets become more friction-free, or will there be less trust, and will this work as an impediment in the market? Will assets be priced more or less correctly, assuming you can figure out what finance people might mean by that? Okay, and so these are aggregate questions. There's I hang out at this place called the Santa Fe Institute. The Santa Fe Institute studies complexity. Okay, whatever that, not simplicity, complexity. Okay, and in particular, so the Santa Fe Institute is concerned with one of the a research theme that is present in many of the research programs at the Santa Fe Institute has to do with the emergence of interesting aggregate and complicated aggregate behavior from the interaction of simple agents, right? And so they talk about complex adaptive systems. And there's a terminology which I've actually found very useful in thinking about social networks that comes from this. And this is the notion of what's called an emergent property, all right? And here's a very nice definition of an emergent property, which I found very powerful in my own thinking, which some physicists at the Santa Fe Institute uttered over lunch one day. And that is, what is an emergent property of the system? If we take some kind of system, and he was thinking of physical systems, we have equations that describe the behavior of the system, right? So we have, for example, in a trading game, right? If we're looking at trading in a market, we might have equations that describe the decision rules that all the various people, all the various traders are using, okay? And so those rules, right, those equations, they describe what's going on at a certain level of granularity within the systems. What do the individuals do, okay? An emergent property of the system is a property of the system that exists at a level which is different than the temporal and spatial scale at which the equations of the system are in fact describing. So if we talk about what is the price, right? The price is not something that exists at the individual level, right? We'll talk about an average market price, right? And that is an emergent property. It is something that exists at a different scale, right, than the the equation, then the description of the system actions, the actions of all the individual little agents. And so we're looking at these aggregate effects of social interaction, the aggregate effects of social networks. This is an important thing to do. So let me turn to an example to illustrate this distinction. So I want to talk about crime. Crime is fun. There's a lot of research in the United States on juvenile crime. And juvenile crime is particularly important, I think, for, I've been talking all this time, I haven't looked at my notes. I have no idea if I'm talking about what I'm supposed to be talking about. So why don't I just actually catch up and do that? And also use this opportunity to take a drink of water. It is only water. If this lecture gets a little funky later on, you'll know I was lying. Okay. So juvenile crime is very interesting because juvenile crime is largely seems to be a group activity, right? So individual kids sitting at home doesn't say, well, let's go and knock off a grocery store or something like that, right? It'll be a group of kids who will talk themselves into it or something, and so this is one way in which juvenile crime is actually different from adult crime, and it's it is a kind of a peer-mediated phenomenon. Now, this is in fact, this turns out to be a difficult thing to measure. And let me see if I have in my notes here what I wanted to say. Yeah, here it is. So juvenile crime is something that actually mostly appears in groups, but there's a question about whether or not groups are actually causal, which is to say that if you could kind of drive around at night and break up groups, which is what police in some American cities actually do, like Trenton, New Jersey, that somehow this would cause juvenile crime to fall. And the reason that the causal importance of peers has been contested by some delinquency experts is because they say, well, sure, kids do crimes in groups, but kids do everything in groups, right? So they go bowling in groups, right? They go to parties in groups, right? They, whatever. And since the group character of delinquency is not any different from the group character of any other legal adolescent behavior, it's not clear whether groups are causal for delinquency or whether, I love this word, most of you probably don't know this word, epiphenomenal. It's something, it's excellent word. Excellent, it's a great word, right. So it's just another phenomenon that happens to come along with this, with the phenomena of juvenile crime, and is not a cause of it. So how would you untangle this? Well, the way an economist would untangle this would be to build some kind of model, and that's actually what many sociologists would do too, and in particular these two guys, criminologists, I think, Menace and Harris, wrote this paper on this in 2001. They had some data on juvenile crime in Philadelphia, and I'm not going to talk about this in any detail at all. Let me maybe hit the little button now. But I just want to offer this up as an example of a micro-study. The question is simply, okay, are individuals more likely, right? So the question that they asked was this phenomenon called recidivism, which means that if you committed a crime and you maybe been gone through the court system for it and all of that, and gotten whatever punishment the court metes out. Now the question is, do you commit a second crime? Right, and if you are, that is an instance of if you have, that is an instance of recidivism. There's probably a verb called recidivated or something. Is there? I don't know. A horrible word. It sounds like a neologism to me. And so what they wanted to know was, in this study, was how did group behavior affect the rate of recidivism? So what they actually wanted to do is they wanted to say, let's take an individual and ask whether being surrounded in some sense by other individuals who were, we'll call them career criminals, okay? People who are on their second crime or third crime or something like that. If you have some of them around you, are you more likely to commit a crime? So what would you do? You would do some kind of logit estimation, and that's what these guys did. And I'm not going to talk about these numbers at all. I am not. I'm happiest in high-dimensional Banach spaces. I'm not good with one-dimensional spaces containing things like numbers. Okay. You can see here that what these are. These are logistic regressions and models that included a variety of different variables. I don't want to talk about this. There's more detail in the notes if you actually want to read about this. But the point here is that the object of study is the behavior of the individual. Okay. Now there is a hint of an emergent property as well in this study, because you think that if individuals, and it turns out to be the case here, so their notion. So let me back up and say that there was a notion of what does it mean to be surrounded by other kiddie criminals, right? What it means is that you live within a kilometer. I think that was the distance. So you live within and why they use kilometer in the United States, right? Well, no one knows what kilometer means. That's interesting. But they said that they counted the number of people who were known second offenders, right? Recidivists who lived within a kilometer of you. Right, and the question they wanted to ask was, well, if you live in a neighborhood, neighborhood meaning a kilometer circle containing a lot of people who have recidivated, are you more likely to commit a second crime as well? And the answer turned out to be yes in their study, right? And now you would think if that's the case, you would actually see an emergent property, a kind of spatial pattern to crime, all right? Because if people who are not surrounded by recidivated individuals are not themselves likely to commit another crime, then there should be these kind of blank areas where there's not a lot of crime, and then these areas where maybe crime is much more dense. There should be some kind of spatial clustering, and in fact, that's what we see. This is a map of the city of Philadelphia. By the way, the data that they had for this were all people who went through a juvenile procedure and were put into a variety of criminal court programs. The city of Philadelphia mandated the collection of this data in order to evaluate the programs, and these guys, who I think were at Temple University, got a hold of the data to do this kind of study. And what you see here is if I hit the right pointer here, clear evidence of spatial clustering, which is to say we have these regions where there's a lot of people, there's high probability of juvenile crime here and here and here, and this is controlling for all the things that you would want to control for. These are kind of clusters of low probability offenders, and then I don't know what is actually going on. I don't remember in these areas where there's not a significant cluster of any kind, but there's clearly a spatial pattern here that doesn't look smooth and uniform and random. And that's an example of an emergent property. But most of the focus here is on what is the individual doing? What is going to make a kid commit a second crime? Okay? Different study. This is a well-known paper by Ed Glazer, Bruce Sacerdote, and Jose Schenkman. It appeared in the QJE, but it is a really good paper. It's a really interesting paper. Let me say that. There is an interesting fact if you look at crime data in the United States, and that is that if you look at the variance of crime rates across cities, it's surprisingly high, right? And by surprisingly high, what I mean is that if you thought that controlling for everything in sight, criminal activity was IID, okay, which is to say that you flip a coin to decide, an independent coin, for each person to decide whether or not they were going to be a criminal, the probability being determined by characteristics of that individual, you would see much less variance in the aggregate data of city crime rates, cross city crime rates, than you actually see in practice. And so Glazer, Sacerdote, and Schenkman asked, had the insight to say, well, what could cause this kind of higher variance? What could cause this variance is that if in fact criminal activity is not an independent choice. If the fact that you commit a crime makes it more likely that I commit a crime. So they're trying to explain an aggregate feature, right, of an aggregate measure of criminal data set. Why, for example, if you look at San Francisco and New York and all these different cities, you see a huge variance in the crime rates. And, and that's the question that they wanted to ask. And so they built so they didn't actually build a model, they told the story, okay? And the story is a little bit of a mathematical story, so I'm going to tell you the story now that they built. So this imagine a infinitely linear city, okay? Manhattan going on forever, okay? We have, actually, I guess it's a city of size 2n plus 1. Only an odd number of people can live in the city, all right? And individuals are of three types, okay? And remember, this is not a model, this is a thought experiment, okay? And what they want to do is they want to motivate the idea, okay, that imitating or learning from or being influenced by one's neighbors, so to speak, in social space, right? Not necessarily physical space, but in social space, learning from one's neighbors, learning from one's peers, can in fact cause the kind of correlation, cause a lot of correlation within cities, which is going to lead to greater variation across cities. That's what they wanted, that was their idea. So here's the thought experiment that they performed. We have these 2n plus 1 people living on a line. We're going to imagine that we've got a small number of people who are very saintly individuals, and they're always good, okay? And then we have another small number of people who are evil, okay? They just are criminals, okay? All right, and they want to go out and commit crimes. And then most of us, right, are easily influenced by the person on our left. Okay. Because it's harder to do this model if you're also influenced by the person on the right. But the paper contains an appendix that does that as well. Okay. And so now, but looking at it this way, it's easy. This is actually very clever because it's very easy to see what's going on, right? You don't need a higher degree. So here we have, for example, so we have these people who are type zeros are the saints. So we have the saints, we have the sinners, and then we have the conformists, the people who imitate the person on the left. Okay. So you can see here that we have here red. It must be a sinner. Okay. And because this person commits a crime no matter what's going on, right? Well. Our fellow here looks to his left, sees a sinner, so he's going to sin. This person looks to his left, he sees a sinner, so he's going to sin. But what about this guy? This person is a saint. He doesn't care about the person on his left. He's just going to do good. Okay? And now we go on. What about the person to the right of him? He looks to his left and sees a good guy. He's going to be a good guy too. Well, now you can imagine how this is going to, this correlation is going to change the aggregate statistics. And let's actually look at that. You can do the usual the usual calculations. Let's see. So the expected, you might say, what is the expected action of an individual, right? So let's code things so that 0 is being good, 1 is committing a crime. P0 is the fraction of good guys, P1 is the fraction of bad guys. If everybody in the population were either good or bad, right, the expected action would just be P1, right? Well, here, of course, the expected action is essentially the same. It's the conditional probability of being good, given that you are of some type, either good or bad, right? So that's P1 over P0 plus P1. Right, so that's the same thing as you get in the usual ID model, but the variances blow up. Okay, and you can work through the calculations. I'm not going to work through them here. But the point is that the smaller is P0 plus P1. So let's imagine fixing the odds ratio of being good to being criminal. Okay, but now let's make let's make P0 plus P1, the probability of being a committed type, very, very small. The more imitators we have, right, the higher the variance is going to be. All right, and that's what this is. Showing us here. So the smaller is P0 plus P1, then the larger is 2 minus pi divided by pi, which is the variance. Okay, and this is just an elementary calculation. I don't do elementary calculations. When you're an experienced teacher, you learn never to compute at the board. Okay? All right, it can only go wrong.
Yeah, only bad can come.
Right. All right, so so here we have an example, again, now of something different, of a model which is now trying to explain an emergent property. The whole subject of this is an emergent property. So these guys now go a little bit crazy, and they actually wrote another paper where, you know, anything that looks like a deviation from normal, you know, from the IID world is automatically due to some kind of peer effect, and they showed that it must be right because when you look at incidence of cancer in the population, there is no peer effect, but when you look at other things, there is a peer effect according to this measure. So they kind of went a little overboard with this, but this is you know, I think a very nice idea, and in fact, so this idea of looking at variance as a way of identifying the presence of peer effects of social interactions has now become an important method. In particular, this is, I think, the source of what's called the variance contrast method of identification, which is the subject of Brian Graham's job market paper, and a very nice paper in Econometrica on this topic, and has been applied to studies of educational outcomes, among other things. So, and here's its beginnings. All right, more stuff. There are a number of empirical problems. I'm actually going to spend much more time talking about empirical work than I should, given that I am the only non-empirical economist present in this entire summer faculty, right? And I really should be sticking with my comparative advantage. But my view, there are no theorists in the room, is that correct? Would anyone like to join me and say, yes, I'm a theorist? No, okay. It's really lonely here. Okay, but I'm going to make you feel good because I'm going to tell you that, right? And you can tell your friends, tell your theoretical friends that I said this. Okay, that economics is an empirical field, right? And the purpose of it's an empirical field, and the purpose of theory, right, is to illuminate, right? Is to illuminate empirical work to make. In some sense, I think, to make possible empirical work, right? So theory helps us in many different ways by telling us what we can measure, suggesting what we should measure by suggesting certain relationships that we should be looking for. But at the end of the day, right, theory and theoretical econometrics as well, okay, is there, right, in order, right, to help people actually estimate stuff, okay? So I'm going to spend some time talking about empirical work. And I would just let me warn you now that I have actually never done empirical work, okay, except for required papers in graduate school. Okay, Tom Rothenberg would actually like me to rewrite the econometrics paper that I wrote for him way back when. So there are a number of problems that we need to be sensitive to when we're building models of social interactions. There's the problem of unobserved correlated shocks. There are problems having to do with the fact that the network is, we like to talk about social networks, but social networks are not fixed things. They themselves are the outcomes of social action. And so there are a variety of empirical problems here, or you know, problems in going to data. I think actually that I've written a bit about the third problem, which is distinguishing so-called endogenous and contextual effects. And we're going to come back and talk about that later if there is time, so I'm not going to talk about that now. The problem of unobserved correlated shocks, right, is I think very important. So let me give you an example. The aforementioned Bruce Sacerdote did a study of what happened to students who were in their first year at Dartmouth University where he teaches. So Dartmouth University assigns roommates. So students live, Dartmouth is in the middle of nowhere, right? It's cold, it's in the mountains, it's in New Hampshire somewhere, right? No one is from Dartmouth, right? Except the faculty, I suppose, right? So kids come up there and they have to live in student dormitories. And the university assigns students to each other, assigns roommates randomly, literally randomly, random draw, okay? No opportunities to say I want to live with my friend from high school or anything like that. It's all random. And so this is an opportunity for a great experiment. And so Bruce and his co-authors did, was they wanted to look and see whether outcomes in the first year of college, educational outcomes, how well students did, whether there was a peer effect present, right? So in other words, they wanted to see how likely, what was the correlation between your performance and your roommate's performance? And you might think, for example, well, if I do well, if it is the case that, so one kind of causal effect you might imagine is that I have a roommate who studies really hard, and he's setting a good example for me, and therefore I study really hard, and I end up doing better than I otherwise might. And of course, at those moments when my roommate's attention is flagging, he looks over at me and sees me working hard, and so together we boost each other up, okay? Or on the other hand, right, you might imagine that my roommate is a party animal, okay? And consequently, and he's always dragging me out to the bars with him and all of that. And because he has such a willing person to go to the bars with him, right, that makes him more likely to go to the bars as well, and so we sync together, right? And that seems like a peer effect, right? So we get this bad joint outcome, right, because of this peer effect. We're independent guys, but the guys who live next to us have this really loud stereo that they're playing 24 hours a day, and therefore we can never study, all right? So that's an unobserved, right? That's an unobserved correlated shock, an unobserved shock that hits both of us. And a challenge in estimating social interaction models is to sort out that kind of thing from a real causal effect. And some people say that this is the biggest challenge in actually doing that. Endogeneity of the network. Let me tell you one very brief. This is another Bruce Sacerdote story. Bruce Sacerdote and co-authors did some research at the Air Force. And the Air Force divides people up into groups when they come, and they study together and do things together. And the Air Force wondered if there was a way of organizing the students so that they could boost student performance. Okay, and just to cut to the chase, so these guys came out and they did some work. They looked at some data, collected data, looked at it, and they made some observations about how you could assign students to these large groups, brigades or something, I don't remember what they're called, these large groups, that would then enhance their performance. So the Air Force said, fine, we'll do that. They did that, and what happened was that performance just tanked, okay? How could any economist be so wrong? Right? Economists are never wrong. So the way they were wrong, right, was that this is a very, very large group that students were assigned to. I don't remember how many there were at the Air Force Academy, 4 or 6 such groups. But of course, just to say that you're assigned to a group doesn't mean that everybody in the group is your friend, right? And there is a social network within a group, right, that might actually be mediating peer effects. And what they discovered was that, or the claim is that, when they reassigned the groups along the ways that the researchers suggested, the students organized themselves within the group, the large group, so they wanted to have mixtures of good students and bad students based on previously existing test scores and stuff like this. They wanted to have a nice mix so that it would boost up the bad students. But what happened was that all the good students hung out with the good students, and the bad students only hung out with the bad students, right? And consequently, all the negative effects of being a bad student was magnified. Right? And so you get just the wrong kind of thing. So what's going on here, right, is that the social network that we observe, right, or that we pretend to observe, is not necessarily the social network that actually exists. If we go back to Menace and Harris, okay, to say that we're going to look at the number of kids who live in a 1 kilometer circle around you who have committed crimes, right, that doesn't mean that they're your friends, right? And so we're only making a guess. And to my mind, I think one of the great challenges, maybe the greatest empirical challenge of doing empirical work on social interactions is, what can you say when you cannot observe the network? Because the network is very often, in principle, not observable. Okay. Now, furthermore, not only is the network not observable, but it also is in fact endogenous, right? The choices of who your peers are, and the choices of the actions that you take, right, are in some sense connected. They co-evolve, right? They move together. If we have time, there's a very nice study that I might mention later on about that was actually done in the 1970s by a social worker who went into schools and kind of looked at by interviewing people over time, tried to trace out whether action followed friends or friends followed from actions, and for different activities, she found it went different ways. So we need to think about these kinds of things. And having said that, I'll say that the state of modeling today is really not very sophisticated on these kinds of things. I'm not going to talk at all about how one would build models to account for endogeneity of the, endogeneity of the network. There have been some recent papers by theoretical econometricians who take an idea the difficulty is, how would you build a game theoretic model of network formation, of choosing your friends, right? We don't really have any idea of what the game is, right? And therefore, it's really hard to imagine, right, what a Nash equilibrium would be. And when I say we don't know what the game is, I mean that we don't even know what the strategy space is, right? The strategy space can't be a link in a network, because maybe it takes two of us to establish that, right? So having a description of the game, even at the crude level of a normal form game, is a very difficult thing to do. So there is kind of a shortcut to modeling. Many of you have heard of the name Lloyd Shapley, right? Anyone have heard the name Lloyd Shapley? No one's heard the name Lloyd Shapley. Lloyd Shapley, raise your hand, right? A few of you, 1, 2, this is really, the guy won a Nobel Prize, right? With Al Roth, okay? Oh! Okay, one more time. Lloyd Shapley. Okay. All right, so Lloyd Shapley is actually the smartest individual that I have ever met in my life. Lloyd Shapley, I'm in awe of Lloyd Shapley. So he and a guy, a mathematician named David Gale, wrote a paper many years ago on college admissions and the marriage market. Right? And what they did was they had an idea. They wanted to talk about. Imagine that we have a group of men and a group of women, and they're going to marry each other. What kinds of outcomes, who would we expect to see linked to whom? What kind of marriage patterns would we expect to be stable, right? And so they came up with the following idea: a stable matching of men to women, of women to men, is a matching where there is not a man and a woman who each prefer each other to their own assigned mates, right? And any matching that has the property that no such people exist, okay, is a stable match. And then they proved a lot of things about the properties of stable match. For those of you who are interested in labor and macro labor, right, you know this idea, right, because it's been used to talk about matching firms to workers, right? So this is a big deal, okay? And this was the origin, by the way, of one of the origins of the market design literature. And therefore, although I think it was actually one of the smaller contributions of Lloyd Shapley, it is the reason why he got the Nobel Prize. Okay. Lloyd Shapley also invented the core and stochastic games, among other things. Okay. So, so Matt Jackson and Asher Malinsky wrote a paper where they took this idea and they extended it from what we would call a well, I've lost the term. So we here, this is a special kind of graph that we have with men and women, right? Where men can only match with women and women can only match with men. How might we do something like this more generally, okay? Where anybody can match with anybody. And so what Jackson Walensky said was, well, suppose that everybody has a utility function over graphs, okay? Now we can imagine the same kind of stability concept, right? And what would that stability concept look like? Right, that stability concept would have the following kind of property, that there would be no link missing, which, if it existed, would make the two people at either end of the link better off, okay? And furthermore, no one has a link to someone that they don't want to have, okay? And this is a general kind of a generalization of the Gale-Shapley idea. And this is a way of talking about, and it's a way of talking about endogeneity of a network or of a social graph or something like that, without actually specifying where it comes from. Because the idea is simply that whatever the game is, whatever the Nash equilibrium is, right, at the end of the day, it was likely to satisfy these properties, namely that no one has a link that they really hate. If you had a friendship that you didn't like, you dropped a friend. Okay? And now the question is, well, how could you actually take an idea like that to data? And it turns out there have been a number of recent papers in the last 2 or 3 years, mostly by new PhDs, right, who have, including a student at Cornell, a student of ours, a student of Francesco Molinari's, Junsun Kim, look out for him, a number of people have built models, right, econometric implementations of this, and actually seeing how one can estimate properties of the value functions by actually looking at the networks that you observe. So there are strategies for talking about endogenous networks, but they're very, very complicated, and so we're not going to talk about them more today. All right, so here's a plan for what I'm going to do in the time remaining to me. I have all these topics, and guess what? I'm not going to talk about them all. In fact, this topic here doesn't even exist in the notes. This is something that I wanted to write about, and I wrote it down there so that I would read up. I have a point of view on what this literature should be like, and where there should be some, on what should be done in talking about community structure and graphs, and then I went to look at the literature to find where my ideas were, and I found that they're not there. So that's on hold. We're going to talk about some of these things, between now and 5 o'clock. Okay. So let me begin by the next part here by actually talking. We're going to do some mechanical things. We're going to talk about graphs. How do you describe graphs? Right? What is it that people measure when they measure graphs? It's interesting to me that so much of what we've talked about for the last day and a half has actually had to do with measurement. Okay? And I keep thinking, well, how can we do that? Because there's no measurement without theory. We haven't talked a lot about theory. But here we're going to talk a lot about measurement again. Okay? What do you look at when you look at a graph? Okay? So to begin with, what is a graph? A graph, a directed graph. There are different kinds of graphs. Okay? So what I'm going to do, here's all the chat. Let me just draw a picture. We have these little things, and they're called nodes or vertices, right? And then what we do is we draw some arrows, right, with an end at one node and a beginning at one node and an end at another, and that's a graph. Okay, so it's a set of vertices. These are the circles, and a set of edges. And an edge is an ordered pair that goes from its beginning to its end, from its beginning to its end. Okay, and that's all a graph is. It's just these objects. Okay, and what this indicates is there is a link from some kind of connection from, if this is V and this is W, we have a link from V to W. Okay. Now, what that link means depends upon, of course, the application that we have in mind, right? And there are many, many applications of graphs and to social phenomena. Some of you might know about a lot of the work on financial networks that's been done, right? Where this link would represent some kind of financial obligation, right? And it could be a friendship link, it could be a family link, so on and so forth. Now, a number of graphs have the property. Some graphs have the property that whenever you've got an arrow going this way, you've got an arrow going back, right? And if that's the case, what that means is that whenever W influences V, then V also influences W, and we call such graphs undirected graphs. And then what we do is we just dispense with the arrows, right? We don't need arrows anymore, we just say that this is now an unordered pair, right? It's got an edge from V to W. And what do they look like? This is the moment when I usually grab my shirt sleeve to erase the board, but A, this is a whiteboard, and B, I don't have shirt sleeves. Okay, so you might have something that just looks like this, right? And you've seen these pictures before, I'm sure, right? How many of you have actually read any literature involving social networks? Just raise your hands. Oh, a few of you, but not too many. Not too many, okay. Well, you've got a large reading list, right? Okay. You didn't read it all before you came? Okay. All right. So the Easley-Kleinberg book is a very good place to start. Okay. Easley is an economist. Kleinberg is a computer scientist, and that book comes out of a course that is taught at my university to freshmen and sophomores on social networks. And so now, if you look at that book, you can see what we think is appropriate to teach freshmen and sophomores. Okay, so they learn all about Nash equilibrium by the end of the book. It's really good. Okay, so I've now described what a graph is, an undirected graph. A feature, an important character of a node in a graph is how many people is it linked to. And by the way, I'm largely going to talk about undirected graphs, simply because the terminology for directed graphs is more complicated. Okay, so the degree of a node, right, is how many. The degree of a node is how many links does it have. So here's a node of degree 1. Here's the node of degree 4. Here's one of degree 2. You get the idea? Okay. Now a path. What's a path? Well, a path is an obvious thing. You start here, you march down this link here, you go here, right? That's a path, right? Here, 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 then down here, that's another path, right? Here's a path that's got a loop, all the way up to here, down here, and then back, okay? So these are all paths, right? What is the shortest path from here to here? There's lots of paths. You can go this way. You can go this way to get to here. You can go all the way around and hit everything before you get here, but the shortest path is 2 links, right? That's called a geodesic, right? Just like, remember from geometry, right? The shortest curve between any 2 points on a sphere is called a geodesic. It's the same idea, okay? This is an example of a connected graph because there's a path between every 2 vertices. If we have here in this picture, suppose we have 2 other guys down here and maybe a poor little lonely person over here, now we have an undirected, now we have an unconnected graph, and this graph is said to have 3 components. What is a component? We're going to take a connected set of vertices which is maximal in the sense that you can't expand it and still have a connected set. Okay? So here these 2 vertices form a connected set, but it's not maximal because you got to add in this guy. But if you add in this guy, you got to add in these 2 guys. That's maximal. So this is a component. Here's another component, and here's another component. So this graph has 3 components. Okay. None of these components are a clique. What is a clique? The clique is if we filled in all the possible lines, okay, and connected everything to everything in this component, then that component would be a clique. Okay. One convenient way of representing a graph is by its matrix representation. By something called, there's several terms that are out there. Something is called an adjacent, one term is an adjacency matrix. So what do we mean by an adjacency matrix? We're going to make a square matrix where each row corresponds to a vertex, each column corresponds to a vertex, okay? And there'll be a 1 in the ij position if there is a path from I to j, not a path, if there is a link from I to j, oops, and otherwise there'll be a 0, okay? And that is called, that object that we construct this way is called an adjacency matrix, okay? It's also called a social matrix, okay? Even though graphs obviously have imports that go far beyond, social networks, right? We use graphs to describe biological networks. We use them to describe all kinds of different things, power grids, so on and so forth. We use them in physics, and nonetheless, this object is sometimes called a social network. If we're talking about undirected graphs, whenever there's a link from V to W, there's a link from W to V, so that matrix is going to be a symmetric matrix. Okay. Why are these things interesting? Well, so imagine for a moment the matrix product we have an adjacency matrix. Now imagine the matrix product. What is the matrix product of A with itself? A times A. Well, let's just write out what one term is going to be. It's going to be the sum over K, AIK, AKJ. Okay? So the ijth elements of the matrix A squared is going to be this. Well, this is going to be, this product here is either a 1 or a 0. It's a 0. If any one of these terms is a 0, if both of them are 1s, then this term is a 1. So what does this do? This actually counts the number of paths like this. It's the number of two-step paths from I to J. So for example, from here to here, there's this two-step path, and there's, that's the only two-step path, right? From this, it's the only two-step path, so that's not very, that's the only way, it's not very, I can't talk, I have no idea what I'm doing. All right, but you get the idea, right? This is what I always do at this moment, you get the idea. All right, a weighted adjacency matrix, sometimes we're not interested in just the existence of a link, but we might imagine these links have certain capacities. Maybe we're measuring, for example, how much, how informative something is. This might represent a channel of information, right? And maybe, for example, this channel could be very informative or could not be very informative, right? Maybe there's noise in the channel, so we might represent that by a weight, okay? Or if we think about this represents some kind of social network that we can use, for example, to borrow resources. When an individual gets a negative shock of some kind, their individuals might have different capacities for helping us out. That would be, again, what these weights would represent, okay? So we often want to make use of weighted adjacency matrices. Okay. Now, one of the odd things, by the way, about the social network literature, at least the part of it that is spun into economics, is that these numbers are always non-negative. You might think, well, you'd like to have, maybe this is a positive influence in the sense that whenever this guy does something here, it makes this person likely to do the same thing. But we also all can imagine people in our lives that have the property that when this person does X, you're going to do not X, right? Whatever X is, you're not doing it if this guy does it, right? You want, for example, a negative number there, okay? And it turns out that the economics of social interactions largely is concerned with these what we'll call positive spillovers or positive externalities and not negative externalities. And that is a limitation, right? And it's something that it's not a limitation, it's an opportunity for research. Okay? All right. And I'm not kidding. I think it really is. So let me talk, here's just an example of a more complicated graph. This is a picture that Elizabeth saw me copying into my notes this morning, right? When I should have been listening. And this comes from the Easley-Kleinberg book. So here's an example of a slightly complicated graph, just so we can see all of these things at work. We have three components, A, B, C, D, E, and F through M. We have an important thing to talk about, an aggregate property of a graph is the degree distribution, okay? Which is what percentage of nodes are of degree 1, what percentage of nodes are of degree 2, so on and so forth. And so here I've actually constructed the degree distribution for this graph. The smallest degree is 1. We have A and B, and C and D both have degree 1. H here is of degree 4, right? And we've got a bunch of stuff. We've got four people, C, D, F, and I of degree 2, and everybody else is of degree 3. The diameter is the longest, shortest path. Okay, so the diameter we might we might look at the shortest path lengths from any node in a component into any other node in the same component. Okay, we might say, what is the longest of all of those geodesics? The longest geodesic here is 3, and it's from M to I. Okay. Okay, so these are concepts that we want to talk about. And there is a large literature, mostly not in economics, and for that matter, a lot of it is not even in sociology, it's in computer science, where people go out and measure properties of social networks. And what do they look like? Okay, these are things, common network measurements that you'll see. So here we are again talking about measurement. Graph diameter, the maximal geodesic length, the average mean geodesic length, the degree distribution, I've mentioned this, the clustering coefficient. A property of social networks, it is alleged, is that friends of your friends tend to be your friends too. Okay? So what does that mean in a social network? What it means is that if this guy is a friend of mine, and this guy is a friend of his, right, then it's likely that this person is also a friend of mine as well. Okay? So what that suggests is that in social, it is alleged to be a property of social networks that whenever we have an open triangle like this, right, if we're talking about a friendship network of some kind, that this will be closed. Okay? So, and what does that say? If we think about friendship as an order relationship, let's go back to, I'm sure you all want to think about preference orders and things like that. If friendship is an order relation, this notion says that the friendship relation is often, not always, but often transitive, right? That if A is a friend of B and B is a friend of C, then A is a friend of C, right? Okay. Sound familiar? Right? Just think apples and oranges, right? Consumption model, same thing. Okay. So one of the things you might want to measure if you think that this is a sociologist spend a lot of time thinking about this. Oops. How many, what percentage of triangles are in fact closed, right? And there are different formulas for measuring this. This is called the clustering coefficient, and this is measuring the incidence of this transitivity property. Another thing that one talks about is the component size distribution, right? We have a graph with multiple components. We go back to this graph here. We've got a component of size 2, a component of size 3, a component of size 8. Okay? More generally, if we have a large graph, we might want to ask the question, how many different components, how many different components are there, and what is the distribution of their sizes? Models, stochastic models that are used to generate graphs, we get properties like exponential size distributions for components, and these are important things to measure. Here's an example of a social network. This is a fun social network. Has anybody ever seen this picture before? No. Okay.
Yes, one.
One! Tell us about this picture.
I heard that this picture is about a graph of the network in a forum or in a laboratory. I don't remember it clearly. And it shows that there are some people connected with each other in a large components, just like the flowers in the flat, I should say, the north face of the graph. Yeah, and there are also some persons who, if the graph is describing the laboratory research, then there are some people who are just cooperating with each other within a small group.
So your description of the graph is entirely correct, okay? But the origin of the graph is wrong. Okay. All right. So this is a graph, right, of romantic and sexual relationships among American high school students in a particular high school, which is, thank God, left unnamed by the authors. Okay. Behrman, Moody, and Stovall. Peter Behrman, James Moody. I don't know who Stovall is. And this. So why is this an important question? Okay. Well, so what they did was actually handed out a survey instrument where they asked people about their romantic relationships, their intimate romantic relationships over a 6-month period, and then they also asked about incidental sexual contact. Okay, which is to say, who are you not involved with that you were messing around with? So this is the picture that results. And what is striking about this graph is, as you say, right, there is this giant connection component. Okay, now what is important about this? Suppose that you were interested in the transmission of disease, right, of sexually transmitted diseases among groups. Well, it turns out, by the way, that if you look at adult sexual networks, they don't look like this. Okay. But high school sexual networks tend to look like this. There's actually been a fair amount of empirical work on this. And the shape of the network is going to be very important, okay, for trying to, for figuring out how to intervene, right, if you have an epidemic of some kind of sexually transmitted disease, right? And so measuring the things that we've talked about are very important, okay? Let me move on. Here is another graph that actually comes from a high school. This is another paper of Jim Moody. There is an art actually to displaying social networks when one actually studies the network. In this picture, and I don't remember what the encoding is, this is a friendship network in a high school. And you'll notice that that this graph is laid out in 2 dimensions, okay? And the nodes up at the top are older people, and the nodes down at the bottom are younger students, okay? Let's see. The colors, which actually kind of move in the horizontal dimension here, okay, indicate ethnicity. Okay, whites and Hispanics mostly. I think Asians are the reds. No, actually African Americans are the reds, and this high school didn't have any Asians. That was historic, or at least none in the graph. And so what this graph illustrates is another property that distinguishes social networks from other kinds of networks. And this is a property that goes by the name homophily. Okay, homophily is the property that like attracts like, which you tend to be attracted to, you tend to be linked to people who are a lot like you. Okay, in studying social networks, we don't just want to know the shape of the networks. We actually want, so the shape of the networks. This is edge information, right? How are the edges arrayed? Okay, but another thing we want to know is node information. What do the nodes look like, right? And there's a connection, of course, between the content of the nodes, namely the characteristics of the nodes, right, on the one hand, and on the other hand, what the network itself looks like. And we see that in this picture, where you can see that people who are alike in age and alike in ethnicity tended to be connected together. If you could really read this graph, that's what you'd see. Okay. Otherwise, it's a very nice modern art rendition of the node. Okay. Here are some social networks that have been studied, and this is a table that comes out of a paper by Mark Newman, which is on the reading list, and what's striking about this, so here are a number of characteristics that one might measure. These are different measures of clustering coefficients. N is the number of nodes, M is the number of edges, Z is the mean degree, L is the mean geodesic length, the mean distance, the average distance between any 2 people in the graph. What are these? So there's something called the Internet Movie Database. Have any of you ever heard of this thing? So it's an index of all actors and actresses and who have ever, right? So you've heard, So I know that it includes, so the guys who started this did American movies and European movies, then they added in Bollywood movies, right? I don't know about Chinese movies yet. Maybe they're there, I don't know, I'm not a follower of this. But in any event, what they do is they draw a link between two actors if these two people have been in the same film together, okay? So this is an undirected graph. You can see that it has many, many edges. It covers a long period of history, I think going back almost to the beginning of film. And of course, what's striking is that, look at this. There's 450,000 nodes, right? There's a lot of edges, and therefore, perhaps not surprisingly, right, the mean path length between any two people is really quite small, okay? C2 is the clustering coefficient we want to pay attention to, and you can see it's really quite high. That if I've been in a movie with you and you've been in a movie with him, then he and I are likely to have been in a movie together too, right? Okay. What is striking about some of these things is that in all of these things, the mean geodesic length is really quite small. Okay. So if you look at physics co-authorship, again, there's a link between us. If we're the set of vertices of physicists who published. That are picked up in some index of, there's a link between any two people who co-authored. The ratio here of edges to links is only on the order of 5 to 1, but nonetheless, the path length is really pretty small. Okay, and this seems to be a feature of social networks. Now, there is a danger, by the way, in looking at these kinds of things. And saying, there are lots of characteristic properties of social networks here, okay? There's a lot of literature that does that. Why is that a bad thing? Well, the reason it's a bad thing is that the networks that have been studied are the networks, obviously, that are easy to study, right? So you go into a high school and you do a survey, or you go online, right? And you just download the data, you skim the data from the IMDb or something like that. There's lots of other social networks out there that are very hard to measure, and it might well be that the fact that they're hard to measure has something to do with the shape and texture of the network, and so there's good reason to believe that they're not going to look like this, okay? So you're going to find a lot of BS out there about what social networks look like. Right? And what that is really about is not what social networks look like. It's like what the social networks we choose to study look like. Okay? And you can be sure that there's selection bias there.